benim dedim o.
Okay. So it is easy to go back and remember those. So shade libraries are very efficient ways of using the memory. Also, there is one very good, big advantage for the shade libraries. Do you know what it is? Other than keeping the memory, other than using the memory very efficiently, there is another very big advantage for the DLLs, dynamic link libraries. You know what that is? You can change the DLLs, okay? You can change the DLLs without touching the compiled programs. For example, if I did not link my math library statically, but if I link it dynamically, without changing my program, I can come up with an implementation of sqrt function, right? So I can change the DLL, and that makes my program even better without recompiling my program. That's what happens when Microsoft, let's say, patches a security leak with the Microsoft operating system. They just send you the DLLs, and your programs don't have to be recompiled because DLLs are dynamically linked. Okay, they are loaded in the runtime using this mechanism. Again, with the paging, it is possible. All these kind of advantages are possible with the abstraction of the memory, right? Without using memory abstraction, if we are accessing the memory directly, these kind of advantages cannot be used. So abstraction is something useful. It comes with many advantages. Any questions? Bir tane soru sorun ya. Şu ders başına telefonlara toplasam mı ben acaba? Nasıl olur? Ha? Yapayım mı? Çünkü bazen dayanamayacağım. Gelip böyle telefonlara alıp dışarı atasım geliyor.
Hocam, mesela glibc diye bir şey var Linux'ta.
Ne var?
glibc, bunu lib libraryc diye kısaltmışlar. Biz mesela programlarımızı hani mesela matematik library'sinde bir elemle derledik. Yani öyle derledik.
Evet.
Yani matematik library'sini değiştirdiğimizde düzeliyor ama normal programımızı hiçbir şeyle derlemediğimiz halde glibc arkada değişmesine rağmen programımızı gene bir şey ediyor. Yani onun compiler kendisi mi sonuçta onun dinamik etmiş oldu compiler?
Zaten böyle L-LM dediğimiz zaman static link olmuyor ki. Static link yapmak için zorlaman lazım. GCC'de otomatik diğerleri yapıyor. Yap, yani bunu içerisine mesela içerisine sinüs kullanan bir program yaz. Tamam mı? Box size'ına 8 KB, 10 KB bir şey gelecek. Sinüs kullanımı yap, box size'ına yine 8-10 KB bir şey değişmiyor. Onu zorla içerisine koymak için GCC'nin 1-2 tane opsiyonu var. Ben statik istiyorum demem lazım. Dinamik o kadar güzel bir şey ki sana söylemeden zaten dinamik yapıyorum. Yani printf o kadar büyük bir şey ki, fonksiyon ki statik yapsan programların koskoca ama tek satırlık ve hello world yaptığın zaman 3-5 KB oluyor programın büyüklüğü. Evet.
Hocam dinamik library'ler güvenlik açığına sebep olmaz mı? Mesela zararlı bir kodu yer değiştirse.
Yani diğerler işletim sisteminin elinde çoğu zaman. Buradan oraya yerleştirilmesi, yüklenmesi de şuydu buydu. Eğer öyle bir problemi varsa evet. Yani diğerleri değiştirebiliyorsa o zararlı kod, işletim sisteminin permissionlarıyla falan. Windows'da biraz daha kolay. İstediğini yazıyorsun. Linux'ta o kadar kolay değil. Onlar bir yerlerde saklı. Root ilacı okuyabiliyorsun, yazamıyorsun. Evet. Evet.
Peki bu proseslerde çalıştığı zaman aynı birinci kullanımda sıkıntı çıkma ihtimali var mı? Instruction'larla. Instruction'larla aynı page'de kullanıyorlar.
Evet.
Ama data section'ları aynı olmak zorunda mı yoksa section data section ayrı mı oluyor?
Şimdi bak bu page'ler burada hafızanın bir yerinde, burada da paylaşılıyorlar, tamam mı? Bu adamın kendi page'leri, bu page'leri ortak kullanıyor. Hani vardı ya, hani diyordum page, bunun page'leri var değil mi? Page'leri neyi gösteriyor? Hafızadaki page frame'leri gösteriyor. Bunu da page frame'leri gösteriyor. Buradaki sanal page'lerle buradaki sanal page'ler aynı page frame'leri gösteriyorlar. Niye sıkıntı olsun bunu anlamadım.
Yani her proses çalıştığında aynı data section üzerinden...
Data üzerinde değil, data değil bunlar, instruction bunlar. Data değil, re-entered code bunlar hepsi. Aynı anda birden fazla kişi kullanabiliyor, data yok üzerinde. Eğer bir data kullanacaksa bunların şunun datasını kullanıyor bu şeyin. Çünkü adam kendi yeriymiş gibi görüyor bunu, tamam mı? Kendi yeriymiş gibi. Çünkü kendi adres space'inin içerisinde bunu burada çalıştırıyor. Aynen 36K'ymış falan filan gibi görüyor. Bu burada şu numaralı adrese eriştiği zaman oraya erişecek. Ve bir de dediğim gibi buna çok dikkatli yazılıyorlar. Böyle şey yapılmıyorlar. Ne diyeyim? Böyle absolut adreslere bir şey yazmıyorlar. Hep relative yazıyorlar. Position independent yazıyorlar. Kompanyanın o şekilde yazıyorlar. Okay, let's move on. Something very similar to shared pages and shared libraries, mapped files. Okay. When you are reading a file from the desk, okay, with the paging, there is a very nice way of doing this. You don't read the file to some part of your memory. Instead, you issue a system call to map a file onto a portion of its virtual address space. So when you say that map this file to my virtual address space, from that point, you can read that memory address, and all you are reading is actually a file, okay, from the disk. So it looks like you have a very large array of characters or the bytes. They are in your virtual address space, but actually what happens is that you are reading bytes from a disk. Okay, so map files provide an alternative model for I/O, and this is very similar to shared libraries. Okay, in the shared libraries, you are doing almost the same thing. You are saying that, okay, this function SQRT is in this file, and I like to load that file into this my virtual space, my virtual address space, and anybody else can do the same thing too. So with the shared DLLs, okay, with the shared libraries, you are using something like this. The mapped file is the generalization of the shared libraries. Instead of sharing code, or instead of loading the code from the memory, you can load data from the memory too. Okay. So instead of doing explicit reads and writes to the disk and to and from the disk, the file can be accessed as a big character array in memory. Okay. And shared libraries, as I said, are really a special case of mapped files. Okay. Shared libraries and mapped files. Shared libraries are map files that contain only the executable code. So map files are more general. Okay. If two or more processes map onto the same file at the same time, they can communicate over shared memory. So this is a very fast way of communicating between these two processes, because otherwise, since the processes have different address space, they cannot reach the other's address space. But if they are sharing some part of the memory, mapped file memory, that means that they are sharing data in a very, very efficient and fast way. So map files and shared libraries, okay, and shared pages are all related, and they are a consequence of this paging technique, which is very, very, as I said, important and efficient. Yoklama nerede? Söyleyemedim yoklamayı. Nerede yoklama? Göndersene. Getirme, gönder. Okay, any questions? Any questions with the shared files and map files? Okay, let me move on then. Let's move on. Cleaning policy. If we have an available empty page frame, then I don't need any page replacement algorithm, right? When do I use the page replacement algorithm again? If I need to load a page, and there is no page frame available, then I need to replace one of the pages, right? That's when I need the page replacement algorithm. So if I always have clean page frames in the memory, they are always available, then I don't need any page replacement algorithms, right? That makes it very, very fast for me. Okay, if a process needs a new page because there is a page fault occurred, then I would use one of the available page frames. That would be that easy. So the cleaning policy uses that kind of a technique. Says that, okay, The paging works best when there is a good supply of free page frames. So, but I know that my memory is limited. I will not have all the time free pages. So there is a daemon, paging daemon. Okay, it is sleeping all the time. So it wakes up when there is no free pages available, and it clears some of the pages. It writes them to the disk if they are dirty. It makes them available and goes to sleep again. Okay. If too few page frames are free, it wakes up and it begins selecting pages to awake using some page replacement algorithm. So this paging process, the background process, wakes up and it runs this page replacement algorithm, whatever it is using, to make some pages available. So that when the processes need a new page, okay, they don't have to wait for the page to be written to the disk, and they don't have to wait for all the page replacement overhead. They would just use the free page, and that would make it very, very efficient for the normal processes. So this paging under background process is useful for this kind of a solution. So this is called cleaning policy. Always keeping some clean page frames available. Okay. So another additional process, but it's something useful. Okay. Moving on. So when does the operating system involve with the paging? There are 4 cases when the operating system has paging related work to do. The first one is the process creation time. When you create a process, okay, the page tables for that process needs to be created. The space has to be allocated for those page table entries. Okay, so maybe you need to add some nodes to your clock algorithms or the linked list algorithms, whatever you are using, and you need to allocate some page frames for the current process. Okay, that's one thing. That's one place where you need your operating system to do something with the paging. The second time is when the operating system deals with the paging is process execution time. Okay, when the interrupt happens, preemption occurs. Okay, when you are switching between the processes during the execution time, you need to reset the MMU, okay, memory management unit, so that it resets all of its pages and etc. That kind of stuff. And the TLB has to be flushed. And these are all done with the operating system. This is the second time. This is the second function of the operating system with the paging. And then there is a page fault time. Okay, page fault time. When a page fault happens, what do? We need to find which page caused this page fault. Okay, the page number, we need to find the page number first. Then we need to check if there is a page frame available so that we can use that one available page. If there are no pages available, then we need to run some kind of a page replacement algorithm. So this page fault time uses these page replacement algorithm. And at the end, when the process dies, okay, during the process termination time, we need to release all those page frames and table entries, etc. So these are the 4 main cases where the operating system interacts with the paging. It involves with the paging. Okay, so where does the page replacement algorithms work? At what phase of the phase of out of these 4, where do we run the page replacement algorithms? Process termination time. Do you run any page replacement algorithm at the process termination time? No, because you are releasing all the memory. How about the execution time? When you are doing the context switch, do you run any page replacement? Why? When you are doing the context switch, when you do the context switch, after you did the context switch, when you are executing the new process, maybe you need more pages, but process execution time, you don't run any page replacement. Page default time, yes, you are running some page replacement algorithms at the page default. Also the page creation time, if there are no page frames available, then you need to replace some of the pages. So these two, okay, these two times you could run your page replacement algorithms. Okay. Any questions? Okay, I'm moving then. Let's look at this page fault handling. What happens when a number 3 here, page fault time? What happens if a page fault happens? Okay, so when does the page fault happen? Okay, when you need to access some memory. Okay, to access some memory, you need to go to the page table and you need to look up the frame number. When you go there, when you go to the page table, you see that your frame is not loaded. Okay, your page frame is not loaded in the memory. So you need to. That means that there is a page fault. Okay, so the page fault happens. When the page fault happens, the hardware shrubs to the kernel, saving program counter on stack. Okay, because page fault happened. So you go to the kernel, you only save the program counter and maybe some other, maybe a few specialized registers. Then when you go to the kernel, assembly code runs and it saves all the imported registers and all the stack information and everything, okay, into some safe place. That's when it happens. And then the system discovers, at this point, at number 3, the system discovers that a page fault has happened. A page fault has happened. We discovered that a page fault has happened, and it tries to discover which virtual page needed. Okay, that takes some time because this is a complicated process. Page fault happened, you know that, but you don't know which page caused this process. We will look at it more carefully in a few minutes. Okay, so after number 3, we come to number 4. Once virtual address called fault is known, I know the virtual address now. I know where my instructions are trying to reach in the memory. I know that address, and I check if that address is a valid address or not. Okay, if it's not a valid address, that means if the program is trying to access some crazy space, then I need to terminate that process because it is doing some segmentation fault, right? So it becomes, page fault becomes a segmentation fault if the memory it is trying to reach is out of my address space. Okay, okay. So that's one thing. If it's a valid address, okay, system checks to see if the address is valid. Then if it's a valid address, the protection is consistent with the access. Then I can continue. I can continue loading that page or whatever I'm going to do. So first, I need to know if that address is valid or not. Okay. So if the frame selected for the page replacement, if there is a free frame, then I could use it. Otherwise, I need to replace some pages. If the frame selected is dirty, that means it is modified. Then pages scheduled for transfer to the desk. Okay, that means that it's going to take some long time. At this point, context switch happens because the current process cannot continue. It caused some page fault, and it needs to replace a page. But replacing the page will take some time because I need to write the dirty page to the disk. So I would suspend my process. It will wait until the whole frame is written to the disk and the new frame is loaded. Okay, as soon as the frame is clean, a new frame is available. Okay, operating system looks up disk address where the needed pages and schedules disk operation to bring it in. That would cause the process to block again because it's going to take some time. Okay. Then when the process goes to sleep, when the disk operations are done, you get a new interrupt. Okay, disk interrupt indicates page has arrived. Tables updated to reflect the position and frame marked as being in normal state. I would load my frame and I would make all the pointers and reference bit and dirty bit, everything is reset. And I would go to the number 8, faulting instruction backed up to the state it had when it began and program counter is reset. Number 8 is important because when, let's say, when I say move the content of the register A to this address 0xFF76, okay? When I do this, if this number is causing some kind of a, if this number is causing a page fault, that means that I caused a page fault. When I was executing this instruction, and while I was executing this instruction in the middle, I saw a page fault. So my execution of this instruction just interrupted in the middle. So I need to back up the execution of this instruction. Number 8 does that. Faulting instruction is backed up so that it can restart again because it was interrupted in the middle to a state where it had begun and the program counter is reset. Meaning the program counter from this position it moved again back to the top of the instruction. So then faulting process is rescheduled. Operating system returns the routine that called it, and operating system is done. The procedure, the process that was interrupted due to the page fault can start again at number 10. Routine reloads registers and other state information. Returns the user space to continue execution. So when a page fault occurs, it's a complicated process. When a page fault occurs, the easiest part would be there is a frame available, and I would use it immediately. Otherwise, sometimes I need to write the dirty pages back to the disk and load the values from the disk. And remember, sometimes if there is a, see,